let's evaluate this definite integral. So I'm supposed to integrate from minus pi halves to positive pi halves, 2 cosine theta divided by 1 plus sine squared theta d theta. I'm going to proceed with a substitution. And I think I'm going to let u equal sine theta. And the reason I'm going to do this is because I see that sine theta is being squared there, always remembering that when we write sine squared theta, we really are abbreviating what happens when we square the sine function. So I see that nice happy inside function, and even better than that, I see its derivative hanging out right there. So du is cosine theta d theta. That d theta then will be replaced by du over cosine theta. So I see they'll cancel. I could also just look at this and say, well, cosine theta times d theta, well, that's my du. So I could just go on and think of it that way and say, well, that's going to give me a 2 over 1 plus u squared du. I'm going to go on and factor that 2 out front, and then I'm going to worry about what's going on in my bounds. Because both of these integrals need bounds, but now those bounds need to be in terms of the new variable u. So I go back and I use this equation to translate these bounds, which were thetas, into u's. So I need to plug a pi halves into sine theta. Sine of minus pi halves is minus 1. Sine of pi halves is positive 1. That's what that equation does. It turns thetas into u's, and so now I have a new integral that's just in terms of my new bounds. And even better than that, I know an antiderivative formula for 1 over 1 plus u squared. That is the inverse tangent of u. Now I'll have to evaluate that from minus 1 to positive 1. Well, the inverse tangent of 1 is pi fourths minus the inverse tangent of minus 1, which is minus pi fourths. So I have 2 times pi fourths plus pi fourths is pi halves, and so we just get pi. So we've evaluated our definite integral, and that's it for now.